Okay, great. Thank you. All right. Good afternoon, everybody. Buenas tardes. Welcome to week 4 of our satellite training. So just as a reminder, you want to go to the classroom for our class, and you can either access the Python tutorial from the homepage, or if you go to classwork and you click on week 4, semana cuatro, you can click on the link to open the today's tutorial file in Google Colaboratory. So I'll give everybody a chance to do that. I'm not going to click on it because I already have the file open, but I'm going to click on it right here. And when you do that, you should have a file opens that looks like this. So I'll give everybody a chance to do that. And remember, you want to go to the top menu here at the top under File and click on Save a Copy in Drive to save a copy of the file in your Google Drive. And then when you do that, a new tab will open and it will have the copy of this file there for you. And so if you want to run that one, that copy file, I recommend that because you'll be able to edit that file and run all the cells. Okay, so let me just show you what we're going to do today. Let me pull up. So we're going to work with the GOES 16 or GOES East satellite, the ABI sensor, the Advanced Baseline Imager, the Level 2 fire data, and the aerosol optical depth data. So we're going to, first we're going to download the files for 1 hour of observations. So we're still working with our case study event day of November 6, 2023. So we're going to look in the morning from 13 to 1350 UTC. And first, we're going to plot the fire detection, so just the latitude and longitudes of the fires on the topographic map backgrounds, like you see here, just like we did last week for VIIRS, except, of course, the ABI data have the higher temporal resolution. So we have observations every 10 minutes. So we're going to plot that, and then we're going to do the same thing, but for the fire radiative power. So we'll process that fire radiative power, and we'll use the color map to plot the fire radiative power, which again, remember, is a measure of the intensity of the fire. So the higher the fire radiative power value, the more intense the burning of the fires. And so we'll do that on that same map background. And then finally, we'll look at the aerosol optical depth data. And so again, we'll download 1 hour or 6 files, and we will plot the aerosol optical depth data on that shaded map background that we saw last week. And we're going to use the native geostationary map projection of the GOES 16 satellite to plot the data. Okay. Does anybody have any questions before we get started? Any questions about anything? If I can pull back up. Okay, well, when you do have questions, again, as always, please, put them in the chat, either in English or Spanish. And as I see them, we can stop and address them. Okay. All right. So a lot of what we're going to do today a lot of it is overlap from the previous 3 weeks. So obviously there's a lot of similarities between what we did last week working with the VIIRS data, but there are some unique aspects of the GOES 16 ABI data, and that's what I'm going to focus on mainly today. Okay. All right. So again, scroll down. So as always, the very first thing you should do before working with any new satellite product is read the documentation. So I've actually done that for you. I'll talk about some of the things that you need to know. But if you're working on your own and you're working with any other new satellite products, always find the satellite documentation and read it. So that way things like the valid data ranges of the product, any sort of quality flags or data flags that you need to use to screen or process the data, or any known issues about the data that you just have to be aware of, okay? All right, so, you know, setting up Google Colaboratory, hopefully that is very familiar to you by now and in the 4th week. So here's the list of the Python modules and packages. I think they're all the same from the previous weeks. But does somebody have a question? I thought I heard something. Okay. The only one that's different is this last one called the Python Imaging Library. That's a new package that we're going to work with this week. We're going to use that to actually make animated GIF files. As you saw when I showed you at the beginning, those animations of the 1 hour of the maps that we're going to make. So this Python Imaging Library, that's the package we're going to use to make those GIF animation files. Okay, so as always, again, you want to just click on the gray shaded code block and run the block using the little black circle with the white arrow on the left. And that'll just take a few moments. Again, like we have done for the past 3 weeks, we have to install some packages, the S3FS, the NetCDF4, and Cartify packages into the Google Colab instance because they're not part of the standard Colaboratory installation, okay? And then again, once the code is done running for that specific block, you'll see a little green check mark to the left of the block and a little time underneath. That's the time that it took to run the code in that block, okay? In this case, mine is 15 seconds. All right, so let's go down now to the next block. And so let's run that and actually install the Python modules and the packages we need for this tutorial. Okay. All right, and then next, again, as we've done for the past 3 weeks, I want to make some directories. So again, if you go to this left vertical menu and you click on the little icon that looks like a folder, you'll see this opens up the content directory of the Google Colab instance. So let's run these 2 blocks because I want to make new folders or new subdirectories. So one for the ABI files that we're going to download, the data files, and then one called map plots that we're going to use to actually put the image files that we generate of the ABI data. Okay, and then as we saw in previous weeks, I like to name the paths to those directories. And that's just a convenience. It just saves typing when we go to basically download the files or save the files. Okay. Okay. So now the first thing we need to do is we need to re-download the ABI files that we're going to work with. So this is a review of week 1 now, if you can remember back that far, 4 weeks ago. So you remember the NOAA GOES-R program, which is the geostationary satellite program. They also have all their files on the NOAA Open Data Dissemination, or NOD program, on Amazon Web Services. So this is the cloud archive where the data files are. Okay, so if you remember from the first week, there's separate what are called these S3 buckets, or essentially the cloud data directories. So there's a separate one for Goes East, which is the one we're going to work with. And there's one for Goes West, which is currently Goes 18. And then there's another one for Goes 17, which was the previous Goes West. So obviously South America, that's the coverage for Goes East or Goes 16. So we're just going to be working with the Goes 16 data today. Okay. So if you remember, the first thing we need to do is we need to use the S3FS package to connect to the Amazon Web Services S3 buckets. So go ahead and just run this block, and that now gives us our connection to the online data repositories or archives. And we're using this anonymous connection because all of the NOAA data are free and open access. So we don't need an Amazon Web Services account. We can connect and download the NOAA data freely. Okay. Okay, so the first section, I want to cover the level 2 VIIRS files. And so those, if you remember from week 1, those are called Fire Hotspot Characterization, or FDC files. All right. So again, if you remember from the first week, we have to work with the ABI full sector data files. So if you remember, the full sector is the data files covers the full hemispheric disk, so the full area that the GOES-16 satellite covers. And so I'm going to go through some steps where, again, you remember from week one, what we're going to do is we're not going to download the entire full disk files. We're going to actually subset them, and we're going to download the subsetted files. So we're just going to download the part of the full disk files that cover our region of interest in Western Central South America. So I just want to take a second, and I just want to illustrate that for you using I just made some maps of the AOD data, just so hopefully this concept is clear before we go on. So this is an example of the aerosol optical depth data, which we're going to download in a second. We're going to do the VIIRS first, and then we're going to do the aerosol data. So this is the file, the aerosol optical depth file for 1300 UTC. And so it's covering, so the sun isn't up on the left or the western side of the GOES-16 domain, but you can see, the AOD data cover, most of the region of the hemisphere, okay? But you guys as users in South America, you don't need all the data in North America or the Pacific Ocean. You just want to focus in on the data that's in South America. So what the subsetted files, what we're going to do is we're going to do that. We're going to just pull out the part of the file, of the full disk file that covers the region of interest in South America. And we're going to download these smaller subsetted files, okay? So there's two advantages. First of all, the main one is that the data files that you download are much smaller, okay? They're about, I did the math, they're about 70 times smaller than the original full disk file. So it's just, it's just a little bit easier to work with those files, okay? So just so you know kind of where we're going in the next section here. Okay, so this first part is just, again, a review from week one. The first thing we're going to do is we're going to get all of the full disk files, so the original files for November 6, 2023, from 13 to 1359 UTC. Okay, and we're going to use the F3SS, LS command. So we're going to list the files that are in the directory that are set by these variables. Okay, so if we run that, and then we're going to print out essentially the file names for the available files. So there's 6 files you can see, and if you dig into the observation time, you can see they run from 1300 to 1350 UTC. So there's another file every 10 minutes. There's a new observation. So we have 6 files per hour. Okay. So again, these are the original full disk files. These are these files that cover the whole hemispheric disk. So now let's remember, I just want to review how we actually subset those files. So what I did is I wrote 2 functions. So this first one, what this does is that it converts the latitude and longitude information that we enter, because we're going to use the latitude and longitude of the corners of the bounding box of basically the box that corresponds to this location. We're going to enter the latitude, the upper left, the upper right, the lower left, and the lower right and lower left corners of that domain, and that's how we're going to subset the files. But one of the things about the ABI files that's different from the VIIRS files is that ABI files don't include latitude and longitude variables in the actual file. And as we go on today, we'll see exactly how that works. But what this function does is it essentially converts the latitude and longitude that we're going to enter to the variables that are used in the files, which are called X and Y. Okay, so let's run this function. We're not going to get there's not going to be any output yet. And then this next function, what this one does is it uses that the information, the y and x variable indices from the previous function, and then it takes those boundaries that we're going to enter, the upper left and lower right latitudes and longitudes, and it uses those indices to essentially subset the file. And this is where we're actually selecting all of the variables in the full disk file, and we're pulling them out. Okay, and then we're going to, at the bottom, we're going to actually save the file as a new separate netcdf file. Okay, so we're just going to download those subsetted files. And what this is doing up here, all this information, this is just adding, it's changing the metadata in the file so that when we open the file, we'll know that we've changed the geospatial domain of the file. These are metadata that are in the file, and we'll take a look at those when we open up one of the files. And then we're going to add a metadata comment that basically says that we subsetted the variables in the file from the original file. Okay, so let's run this function as well. So I wrote these two functions here. I wrote those, and now we're going to use them in this next block to actually download the files. So here at the top, this is where we're setting those latitude, longitude corners. Okay, so essentially we're going to be going from minus 30 to minus 5 degrees latitude, and then minus 45 to minus 80 degrees longitude. Okay, that's going to be the corners of our box. And so you just want to set them a little bit bigger than the actual domain that you want to map. All right, so just make sure you don't set them too small. Go a little bit bigger. It's better to have a little bit extra data than to not have enough. And then here, this is where we're actually going to do the subsetting. So, so this file list, this is the list of, if I scroll back up, this is the list of the directory paths to the Amazon Web Services node for the full disk sector files, okay, that we found previously. So what we're going to do is we're going to loop through each of those files. We're going to print the file name just because I like to keep track of what's going on. Then we're going to, with these two lines, we're going to open each file remotely. So we're not going to download the original full disk file. We're going to open it remotely, and then we're going to subset it using the two functions that I just showed you. And we're going to do that for all 6 files. And then when we're done, we'll see we'll print done. So we'll know. Okay, so if you run that, you'll also be able to see, so the files, pull them up here. So you can see that went really fast because the VIIRS files are pretty small. So it goes quickly. So you can see what we did is we printed out the original file names as the code was looping through. And then we downloaded, if I can pull it all the way out here. So here we see the 6 subsetted files that we downloaded. And what I did is I renamed the subsetted files. Hopefully you can see I added after the FDCF, which stands for the FDC, the Fire Hotspot Detection Characterization Files. F stands for full disk. I added sub SUB after that, just so that when we looked at these files, we would be able to tell the difference between them, the subsetted ones, and then the original files, just so none of us would get confused. But then the file name is otherwise it's identical. Okay, it's got all the same components. All right, does anybody have any questions about that? It's a little complicated, but I think it's just a nice option for users in South America because you don't need the whole full disk file. You just need the part that covers, the region or the countries that you're interested in. Okay, great. Okay. So now let's go on. And did that run everybody okay for everybody? So does everybody have the 6? I should probably make sure. Does everybody have the 6 subsetted files listed here under the ABI files directory? Maybe you could just put something in the chat or give a thumbs up. Make sure everybody's has the files before we move on. Okay, great. Thank you. Anybody else?
Buenas tardes. ¿Todos han podido obtener los 6 archivos que Amy ha obtenido? ¿Alguien ha tenido algún problema?
So do you think everybody's okay, Laura?
Yeah, I think so.
Okay.
Go ahead, please.
Okay, should we go ahead? Okay. Oh, here we go.
Yeah,
Okay.
everything is good.
Okay, now they're saying it's good. Okay, thank you. I just don't want to leave anybody behind. Okay, thanks everybody. Okay, so now let's actually open up one of the files we just downloaded, and we want to take a look inside and make sure we can find the variables that we need, and that we understand the valid ranges of the variables, their units, and their data types. So again, like I said at the top, you want to make sure you read the documentation. So in this case, I've read the documentation for you, so I can tell you what we need to know. But again, I'm looking at the Go16 FDC README file. So the science team recommends that operational users that have a low tolerance for false alarms, meaning the satellite sensing fires that don't really exist, that's a false alarm. So I know that from talking to Karen and Marcos that you guys definitely are not interested in false alarms. So what we want to do is we want to select what the science team calls good fires. Those are the highest confidence fires. And then something they call saturated fires, which I think is a little bit of a confusing term, but essentially it means a high confidence fire, but the fires were really strong, so like very intense. So there's slightly less confidence in those fires. Okay, so essentially these are the kind of the most confident, two most confident options for fires. I think there's a question. So Ludwig says, is there a limit on how many files we can open remotely at the same time? Well, in this case, we didn't open them at the same time. We opened them one after the next. So we opened one and then we closed it and we moved on to the next one. But in terms of opening them all at the same time, I don't think there's a practical limit in terms of what the Amazon Web Services will let you to open. I think it's just more dependent on your computer and your internet connection. So if you have a slow internet connection, it can be slow to open files remotely. But if you maybe you're at your university or you're at work, you have a fast internet connection, then usually there isn't a problem. So Ludwig, if you wanted to work with ABI data, you would do some sort of loop. And so you'd be going through the month of data one day at a time, and then it shouldn't be a problem. So you can certainly try it and, let me know what you think. Maybe start with, depending on the time period you want, maybe start with just one day and see how fast that goes. And then, build up from there. That would be my suggestion. That's a great question. Okay. Yeah. Maybe let me know how it goes. But yeah, there's no limits from the Amazon Web Services about the data files. It's just more I found the internet speed is a big variable. Yeah. Okay. All right. Right. So we're going to open up the first file, the one from 1300 UTC. And so all this should be familiar from last week. We're just going to use the XR open data set function to open the file, and we're going to list the metadata. Okay. So I should warn you, ABI files have a lot of data variables. So this file, the VIIRS file, has 40 data variables. So they're much more complicated than the VIIRS files. And the big thing is you'll notice under the coordinates, there's no latitude and longitude, like I mentioned before. So instead what you have is what's called the y and x variables. So remember, for any of the coordinates of variables, if you click on the little icon that looks like a file, that'll show the attributes, it'll give you the metadata for that variable. So the y variable is called the GOES fixed grid projection y coordinate. It's in units of radians. And the x variable is the same thing. It's the GOES fixed grid projection x coordinate. So we're going to talk more about the GOES fixed grid projection in a few minutes. But what that is, it's the map projection of the GOES satellites. In this case, it's the GOES 16 satellite. And the reason it's included in the ABI files and not latitude and longitude is just to save file space. So latitude and longitude takes up a lot of space. They're floating point numbers. So, they end up consuming a lot of file. So basically, just to save file space, the GOES-R team includes these X and Y coordinates instead. The other reason is because the grid, the ABI fixed grid, the GOES fixed grid, it doesn't change, right? So this is a geostationary satellite. The grid is always the same. So, it doesn't change based on the day or the time of day. And that's very different from the VIIRS data, right? So every time VIIRS, on one of the polar orbiting satellites makes a new overpass, when it's observing the Earth, the location is always different. So the grid of the files is different for every file. And so that's why the latitude and longitude are included in the VIIRS files, okay? So this can be confusing for, I even find it confusing sometimes, and I'm, an expert. So please, as we go on, feel free to ask questions. Okay, so that's the first thing I wanted to point out. And we're going to calculate latitude and longitude. I'm going to show you how to do that. But I just want you to be aware that we have these X and Y variables instead of latitude and longitude. Okay, so let's open up the attributes. So if you remember, under attributes here at the bottom, this is the global metadata, so the metadata for the whole file. So if you scroll down to the bottom, I just want to point out to you where it says file modified. This is the comment that we added when we made these files. So I just want you to see, where that comment ended up. So we said, we subsetted them from the full disk files. And then we have the indices of the Y and X variables that we used to subset the files. And again, those indices of Y and X, that's the ranges that correspond to those latitude and longitude corners that we entered, okay? All right, and then there's a lot of other information about the file as well, and the product, the fire hotspot characterization. Okay, I'm gonna close that up. So now let's look at the data variables. As I said, there's 40 data variables. There's a lot of stuff in here, but the things that we need are near the top. So these files also have a measure of the instantaneous area of the fires. That's this area variable here at the top, the fire area. Okay, we're not going to work with that, but just be aware that that's there. And also the instantaneous fire temperature. Okay, we're not going to work with that today either, just in the interest of time, but just be aware that that's available if that's information that you might be interested in. Okay, so they're there. So what we're going to be interested in is the power variable. So if we click on the power variable, this is the fire rated of power variable. So we can see the valid ranges from 0 to 200,000 megawatts are the units. Okay. And then we're also going to need this DQF, which stands for, oh no, I'm sorry, I apologize. That's for AOD. We're going to need the mask variable here. Sorry, I didn't be confusing. So we need the mask variable. So this is the fire mask, okay? So for each pixel in the file, each pixel has a value for the fire mask. And you can see the flag values. Here they all are, okay? And then underneath are the corresponding meanings, okay? It's a little bit hard to read them all. But again, this is where we're going to be selecting the fire mask values that are either equal to 10, 30, 11, or 31. Okay, and if we look at the meanings, so we can see for 10 is where it is. It's a good fire pixel. If I can highlight it here, it's a good fire pixel. That's what 10 corresponds to, and then 11 corresponds to a saturated fire pixel. Okay, so again, the terminology is a little confusing, but it's the main thing we need to know is that we want to select the fires that correspond to 10, 11, 30, and 31. Okay, and I'm going to show you how to do that. Okay, all right. So, and then there's a whole bunch of other things. Where else? Oh, I want to show you the geospatial lat-long extent. If we click on that. So this is, I'm on the geospatial latitude and longitude references. So again, these values right here, these were, if you remember when we subsetted the files, we changed these values from the full disk. So these now correspond to the latitude and longitude ranges of our subsetted domain. Okay. So that's another thing that's slightly different in these files. What else? Oh, I wanted to show you the GOES imager projection. So the GOES imager projection, it's the 1, 2, 3, 4, 5, 6th variable down. Okay. So this has information about constants, about the geostationary satellite projection. So it has things like the central longitude, which is minus 75 degrees, so 75 degrees west. It has information, essentially the perspective point height, that's the height of the satellite above the surface of the Earth. And then some other information. We're going to use this information to calculate latitude and longitude. And also we're going to use it to calculate the geostationary map projection when we plot the AOD data. Okay, so I just wanted to point out where that data was in the data variables. Okay. All right, so let's look a little bit more closely at the power data array, which is the fire radiative power data. So this brings us to our first exercise. So if you remember, for the past 3 weeks, every time we've opened up a new file, that's one of the things we want to do. And we actually want to see what the data, like an example of what the data look like. And we use the XR data array values function to do that. So hopefully this is review for you guys. So what I want you to do is I want you to remember back to last week and the week before about how you do this. So how do you view one of the data arrays as a NumPy array, so that we can see like a little example, a snippet of the beginning and the end of the data array. So I'll give everybody a chance to do that. And there are answers here if you can't remember, but try to remember how to do it before you look at the answer. So while folks are working on that, Marcos and Laura, was there a technical problem before? Do I need to repeat anything?
Amy, I have a problem, but it's my problem, not. I think everybody else were correct.
Oh, okay. Okay. I just want to make sure. I don't want to lose anybody. Okay. Were people able to see how to view the power data arrays and NumPy array? Do you guys remember that from? Was anybody able to do it? So remember, all we do is we use, so it's the format is XR data array.value. So we have the name of the array, which in this case is DS, which stands for data set power. and then we append values after it. And we run that. And, oh, go ahead. Question?
The name is case sensitive, right? Power.
Power, yeah. So power, it has to match the name in the file. So sorry,
Okay.
scroll up so we can see. Yeah, that's a good question, Marco. So we can see power is capital. It's capital P. So we have to, yeah, it's case sensitive in the sense that it has to be the same spelling as the variable in the file.
Thanks.
Sure. No, thank you. Okay. Okay. And so we can see that's not super helpful, right? Because, and we saw this, I think, with some of the data last week as well, because the values of the fire rate of power are either missing or invalid at the beginning or the end of the data array. So they're just showing up as these nans. So what we can do is, same thing we did in past weeks, we can use NumPy to get the nan min or the nan max values. And so if we run this, that'll essentially give us the minimum and maximum values in the data array, ignoring any nans. Okay. So a couple of things. So we can see the minimum is about 3.5 megawatts, and the maximum in this particular data array is a little over 1,100 megawatts. And so that's good. They're floating point numbers, which is what we expect from looking at the metadata. And they fall, if I'm going to scroll back up, if you remember when we looked at the metadata, the values are megawatts. We expect them to be floating point numbers, and the range of values in the file is within the valid range that's stated in the metadata. So that looks great. Okay. So we're good there. Okay. But if we looked at the mask array, so I don't know if you remember, let's go back actually and look at the mask array again. We took a look at it again, but so if we look at the metadata for the mask, again, this is the fire mask, which has all those numbers. So we look at the valid range, and then we look at all the numbers. Those look like integers, don't they? But X-ray is saying, if we look at the value here, it's saying X-ray is saying that the mask are floating point numbers. They have data type float 32, but that doesn't seem right looking at the metadata. So the reason why there's that discrepancy, so I'm going to scroll back down to our cell. The reason why we have that discrepancy is because X-ray tries to help you out. So in the XR, when we open the file, when we use XR open dataset, there's a default argument, which is called decode_CF equals true. So that's set automatically. And what that does is that it has X-Array automatically unpack and decode any netcdf file using the encoding information in the file. Okay. Most of the time, this is really helpful. We're going to see when we look at the AOD data that it's actually really helpful when it does that. But one negative effect it has is that it reads all the data arrays in as floating point numbers, even if, like the mask array, they're actually integers. So if you kind of suspect something like this is going on, you can use the X-array data array encoding to actually see the original data type of a variable. So let's do that for the mask. So let's run ds mask encoding. We run that. We'll see that there's a whole bunch of stuff that we don't need to worry about. If we go down to the bottom, it'll tell us the original data type of the variable. And we can see that it's int16, which is 16-bit signed integers. Okay, so it's not a floating point number. Okay, so this is just a recommendation with the mask variable, and we'll see with the AOD data, the AOD quality flag. You don't technically have to do this. X-Array can still read the flags as floats, but I just think it's good practice because sometimes with a satellite data product, you'll have a data array that's integers that really needs to be integers if you're going to work with it. And then if it's read as a floating point number, it'll give you a mistake. So I recommend actually always just using the X-array data type as type, or excuse me, data array as type function to convert the data array into the proper type. Okay, so you do the encoding to find out what the correct data type is, and then you can use this function here to actually define a new variable and convert the data array to the correct type. So if we run this, we'll see. So now we'll see that, you know, again, this is printing out a snippet or the beginning and the end of the mask data array that we've now converted to the correct data type. So it's not a float anymore, a float 32. Now it's the INT16 data type. Okay, and then all the other metadata is the same.
Maybe.
Yes, Marcos.
Yeah, just going back a bit. When we were looking at the type at the beginning, this is we're referring to only one variable, right?
Sorry, you mean when we're up here when we were looking at the whole?
Not if you go downward.
Okay.
And you have the print encoding for the mask variable.
Oh, the encoding. Yes,
sorry,
right here.
The answer is there.
So yes. So see where it says ds.mask? So that's where we're getting the mask is the name of the variable. Yep. So if you wanted to do it for power instead, it would be ds here. I can show you how that works. So if you wanted to look at it for the fire rated of power variable, the encoding, you would just do ds power encoding. And it would show you the information. And so you can see that the fire rate of power is in fact a floating point number. So we're good. And that's how X-ray was reading it. And so we're fine with that. We're fine with the power variable.
Perfect. Thank you.
Okay, sure. Great question. Okay. Does anybody else have a question about that? Okay, so again, this is another reason why I recommend that before you start working with a new data set, you always open up one of the files, look at the variables, make sure you understand the data types, the valid range, and you know, make sure everything is the way you think it is before you actually trying to start work with the data. Either you know, analyze them or plot them on a map. Okay. Okay. So next up, so let's actually do that. Let's make a very quick unformatted plot of the fire rated of power data, the power array using X-array. So if you remember, we did this the past 2 weeks. And so because X-array has a lot of the basic built-in plotting functions, and so the map isn't really going to look that nice, but it will at least give us an idea of what the data look like. Okay, so if we run this block, we're going to see a couple of things that are a little different from what we saw last week. So if you remember last week, the FP power variable, which is the fire rated of power variable in the VIIRS files, the VIIRS files, they were one-dimensional data arrays. Okay, so we were able to use the scatter plotting function. And so like we could really see the data a lot better. But because the power variable, it's a two-dimensional variable, so it has dimensions of these X and Y coordinates, the GOES fixed grid coordinates. When we plot them, they're actually being plotted using a p-color mesh plot. So that's why the little dots, I don't know if you can see them, you might be able to see them easier on your computer. There's like these little tiny dots, and those are actually the two-dimensional pixels, the 2 kilometer by 2 kilometer pixels that are being individual pixels that are being shaded by this color map. Okay, so they're a little bit hard to see, but at least it's, you know, we can see with this plot, you know, that there are data in there, and you know, we can see approximately where they lie. Okay, so again, this isn't, you know, this quick plot isn't something you're going to want to use for your data analysis. Is more just like when you're exploring the data, to just make a quick plot and see, you know, what the data look like, or get an idea of what the data look like. Okay. All right. So now the other thing is, so again, you can see there, because there's no latitude and longitude, when X-ray did this plot, it used the X coordinate and the Y coordinate that I showed you. Okay, so now what we want to do is, because we do actually want to plot the fire data and eventually the aerosol optical depth data on maps, we're going to need to calculate latitude and longitude. All right, so I mentioned all this at the top. So this function here that I wrote, this next function, what this does is it takes those X and Y variables and it converts them to latitude and longitude. So this function essentially takes all of the X and Y values in our data file, and it makes the two-dimensional latitude and longitude arrays that we're going to need to plot the data. So if we run this, we won't see anything happen yet. So in this next block here, this is where we're actually going to use the information in our data set, okay, DS, and we're going to calculate the latitude and longitude arrays. So if we run that, then we can actually take a look and see what the arrays look like. So if we look at the latitude array, you see again, it'll print out the beginning and the end of the array. So you can see that we're starting from about -5 degrees latitude and going to about -30 degrees latitude, which is corresponding to, if you remember when we subsetted the files, that's about the range that we set for the data. So that's good. And then if we look at the longitude array, so now we can see it's going roughly from about 80 degrees longitude to about 45 degrees longitude. And again, that's roughly corresponding to the range, the corners that we set when we subsetted the files. Okay. Does anybody have any questions about that? Oh, one other thing I should mention. So again, because the GOES ABI fixed grid is fixed, okay, it's in the name, these latitude and longitude arrays aren't going to change for the files that we downloaded. So if you have a series of files that all have this exact same dimensions, like the files we download, so the fire files and the AOD files that we're going to download, we use the same dimensions. You only have to calculate the latitude and longitude arrays once, and you can use them for all the files. Okay. If you change the dimensions of the file, like you change that domain, then you have to recalculate latitude and longitude. But otherwise, you can just do it once, and then you can apply it to all the files. And that's what we're going to do today. So we just calculated them here, and we're going to use them for the rest of the tutorial. Okay. I should mention, actually, another thing you're going to do is, so if you have a domain and it's set and you don't ever change it, you can actually save these arrays. So you could save the latitude and longitude array in a .NET-CDF file, okay? And, just save that on your computer. And then each time you could just read in that, that file with the latitude and longitude, and then you don't have to calculate it again. So that's another option that a lot of people do. So it's really whatever is easier for you. Okay. All right. So if you remember from the beginning of this section, we actually have to use that mask variable because we only want to select the so-called good fires. And so that's going to be when the mask value is either equal to 10 or 30. Okay. And the so-called, high confidence but saturated fires, and that's when the mask variable is going to either equal 11 or 31. Okay, so we essentially want only those fires, and so we want to apply that mask to the power data array, and then so that's going to give us the fire rated of power, and then we also want to apply the mask to the latitude and the longitude array that we just calculated, and that's going to give us the fire detections or the fire locations. Okay. So remember, we didn't have to do this processing last week with the VIIRS data because the VIIRS science team recommends using all confidence fires. But the fire team for the ABI data says to only select these good and so-called good and saturated fires. Okay, so this function, or this code here rather, is going to do that processing. So let's see how that works. So this is first, we're going to convert the the mask data array to the correct data type. Okay, we saw how to do that. Then what we're going to do is we're going to use this part of the code right here is using xarray. So it's using the xarray data array where function. And I think I have the link. I think I have the link somewhere. If not, it's when we cover the AOD data. I have that function, but it's using this function. And what it does is it's saying that for the the power data array, we're just going to select the pixels where the mask is either equal to 10, 30, 11, or 31. So this vertical line means or, okay? And so that is going to just select those pixels where the mask has one of those 4 values. Then we're going to use the numpy isNaN function. What that's going to do is that's going to create what's called a masked numpy array, where everything that's not one of these 4 values, every pixel that's not one of those 4 values is going to have, it's going to be a Boolean array. And so the value is going to be true. Okay. And then the NP logical not takes the reverse of that array. Okay. And the reason we want the reverse is because we're going to use this formatting here. So where we take the mask, the inverse of the mask, and apply it to the, in this case, the latitude array. What that does is we're using the mask as an index. And so it's going to retrieve only the valid values, the valid entries from the latitude array. Okay, so if we apply it to the latitude array and the longitude array and the fire rated of power array, it's going to return the values for those arrays that only have that mask value. The other thing is it's going to be they're going to be one-dimensional arrays, which we want because we want to use like a scatter plot or a pie plot function to plot the fire locations. Okay, so if we run that, let me show you what it looks like. So if we look at the processed array now, so now we can see this is a one-dimensional array. And so it just has the fire rated of power values that correspond to the mask values of either 10, 30, 11, or 31. And we can see if we look at the shape, we can see it's a one-dimensional array and there's 93 values in it. Okay. If we do the same thing with the latitude, so now we can see these are the latitudes where the fires are that have the fire mask values of 10, 30, 11, or 31. Okay. And it will have the same shape as the fire or the fire rated power array. So again, it's a one-dimensional array and it has 93 entries. And then we can do the same thing with the longitude just to check. Those are the longitude values. And then the shape is going to be the same one-dimensional array with 93 values. Okay. And if as a real double check, we can apply the mask we made to the mask data array. And we can make sure we should have 93 values in there, which we do. And the values should only be 10, 30, 11, or 31. Okay, and so if we look at them, we can see they're mostly 30, and there's a couple of 10s in there. There's a 10 right there, and I felt like I saw another 10 somewhere. I think there's another 10 somewhere. Oh yeah, there we go, right there. Okay, so in this array, there aren't any of those 30 or 31 values, but if there were, we would see them here. Okay.
Amy?
All right, that was a little bit complicated, so people might have questions about how that works.
Amy?
Yeah, Marcos, please.
Maybe you mentioned before this, but these values 30, 10, where they are coming from?
So they're coming from, so it was at the very top of the section. Let me go back there. If I can get back there. So yeah, it's 2 places. Where did I? Oh no, wait, sorry. It was when we were opening the file. Sorry. So it's when at the top of the section, we were opening the file. So they're from the README document. They're probably also in the ATBD, but the README file, and I have the link to it here, has the recommendations for selecting the mask equals 10, 30, 11, or 31.
Thank you, Amy.
Okay. And the reason why is because these are the most, these are very, very high confidence fires, these two categories. And these are the same categories that, for example, the FIRMS site, NASA FIRMS, I don't know if you guys ever used NASA FIRMS, but these are the same, this is the same processing that FIRMS uses. So they're only showing the ABI fire detections that correspond to these 4 values of the mask. They're basically the highest confidence fires. Okay. And again, there's this, the huge, because the flag values go from, 0 to 245, and you can see all the meetings here. It's a little bit hard to tease out all the meetings from the metadata, but they're in there. So that's another place that you can look. Okay, any other questions? Okay. So if not, let's close that data set that we opened. And now let's actually plot the fire detections. So in this next section, so the first thing, we're going to plot them on that same Esri World Topographic Map tiles that we used last week and the week before. So if you remember, we need to run this block. This is just essentially retrieving those map tiles and also retrieving the attribution. We need to give credit to Esri and the folks that provided the data. And so then here, this second block, this is where we're going to actually make the plots. So if you remember, we have to select the zoom level or basically the resolution for the map tiles. So you may want to change this. I liked zoom level 6, but you may like 5 or 7. It's up to you. And then these are the same settings we used last week for fire detections. I think we need relatively small markers. I like them to be colored red and to be squares, but you can obviously, change that and adjust to make the markers appear however you prefer. Okay. So then what we're doing here is we're defining a variable called file list, and we're using the pathlib module to go to the ABI path here, which is the ABI files on the Colab instance, and get all of the FDC files using this wildcard. These little asterisks mean the wildcard. Okay. And then we're going to set up a loop. So for each of these 6 files, that we downloaded, we're going to open the file using Xarray. Okay. We're going to set up our figure. Okay. We're going to grab those map tiles and add them as the background. We're going to zoom in to just the kind of western or central western South America region that we're interested in. Then we're going to process the fire data. So we just saw how to do that. Okay, we're going to change we're going to change the data type of the mask variable, and then we're going to make that fire mask and apply it to the latitude and longitude arrays that we calculated. Okay. Then we're going to, this is I think exactly the same as we used last week. It's just the argument variables are slightly different. We're going to plot the fire detections using the matplotlib pyplot plotting function. Then we're going to pull information out of the file name, the ABI file name, and we're going to use that to make the title for the plot. Okay. We're going to show the plot, and then we're going to use the information that we pulled out before, and then pull out a little bit more information to make a name to save the file. And we're going to save it under map plots here. And then we're going to close the plot and move on to the next one. Okay, so if we run this, so this is going to take not too long. So we'll see, again, as we loop through each of the 6 files that we downloaded, we're opening each file and we're plotting the fire detections on the Esri World Topographic Map backgrounds. And again, I'm using red square markers. And so we can see that the plot title that we made automatically, and I think it's done. Yeah, so mine took 31 seconds. So again, if we come over here under map plots, we might have to finish refreshing. You should see the 6 PNG files that correspond to the 6 plots of the fire detection. So from 13, 1310, 1320, 1330, 1340, and 1350 UTC. Okay, was everybody able to get that to work? Does everybody have those 6 PNG files? I guess I'll leave it there for a second. Maybe give me a thumbs up or. Okay. At least
¿Todos
one
han
person
podido
got
poner
it.
los 6 archivos?
Okay. Yes, people are getting it. Okay, fantastic. Thanks, Laura.
No problem.
Okay. 6 files PNG. That's exactly what you want. Okay, super. Okay, excuse me, just for a sec. Oh, excuse me. Okay, great. So let's move on. So this is going to be the last thing we do, or no, yes, just about the last thing we do, and then we're going to take a break. So I'm just going to make this a little bit smaller. So now let's do the same thing, except instead of plotting the fire detections, let's plot fire rated of power. Okay, so again, this is going to look very similar to last week. So if I scroll down, so again, this is the same. This is the zoom level for our map tiles background. Here's where we're setting the appearance of our markers. So I'm going to keep the same size, and I'm going to keep them as square markers. But remember, with fire rated of power, we use a color map. And so I like the autumn fire map reversed. So remember, if you _R, will reverse any of the matplotlib built-in color maps. And we're going to use a unique color for the data, the fire rated of power data that are greater than the maximum. In this case, we're going to set the maximum as 1,000 megawatts. Okay, and so then this is the same as for the fire detections. We're going to grab all of the data files again that we downloaded, and then we're going to loop through them one at a time. We're going to open each file. Again, we're going to set up our figure with our map projection. We're going to add our map tiles background and the attribution. We're going to zoom in on the Central, Western, South America region. We're going to process the data again, just like we did using the mask. Okay. We're going to get our color map. Okay. And then we're going to use the matplotlib scatter plot to plot the latitude, longitude, and the log 10 of the fire rate of power. So I believe I mentioned this last week, but the convention is to plot the log 10 of the fire rate of power because that just allows for a more intuitive display of the dynamic range of the fire rated of power values, since they can range from 0 to 20,000. And then we're going to add the color bar for the fire rated of power. And this is the same as the fire detections. We're just going to pull out the information from the satellite file name to make a title, and then show the plot, and then save the file. So let's run this. And so now when you run this, you'll get 6 more figures under the map plots corresponding to the fire rated of power. So if I scroll down, you should be able to see the fire rated of power plots being generated. And so they'll look very similar to the fire detections, except instead of just being the solid red color, they're going to be shaded using the reversed autumn color map. Okay, so mine's done. Let's see. Are they all there? Yep, there they are. So now I have, again, 6 new PNG files corresponding to the fire rated of power for 1300, 1310, 1320, 1330, 1340, and 1350 UTC. Okay, so I'll give everybody a chance to generate those. And again, maybe let me know either in the chat or with a thumbs up if you are able to generate the fire rated to power files or plots, excuse me, successfully. Okay, great. All right, looks like at least a few people have gotten it to work.
¿Todos han podido obtener los gráficos que Amy ha producido? Pueden anotarlo en el chat también, por favor. O reaccionar también. Está bien.
Thanks, Lara.
No problem. Oh, yes. Gracias.
Okay, looks like most people got it. That's great. Okay,
Yeah.
So the last thing that we want to do before the break is what I find with the geostationary satellite observations, like we're working with today, it's nice to make those animations like I showed at the beginning, because then you can really see the movement, either the changing in the locations of the fires, or with the aerosol optical depth, you can see the aerosol plumes moving every 10 minutes. So let's use the Python image library to make a GIF file of the 6 fire detections map images. And so what we can do here is here on this block. So this wildcard, this is just a string that's going to be used to select the PNG files in the map plots. So you can see we have 12 PNG files. So we want to have some way to distinguish between the fire detections files and the FRP files when we make the animation. Okay, so this wildcard, I just picked detections. So when we actually grab the files, we're just going to be grabbing the 6 fire detections files. Okay, so that's what this wildcard means. And then you want to enter a name that will for the saved GIF file. And so I just have it as this, basically the same information that's in the individual PNGs, but I just added the range of the time at the end of the file name. Okay, and then for this particular library, we can set the time in between each frame. Okay, in milliseconds. So 1,000 means 1 second between frames. So if you wanted this to be 2 seconds between frames, you would make this 2,000. Or if you want it to be half a second, you would make it 500. So you can adjust that time duration if you'd like. And then this loop setting, so that's the number of times that the animation will repeat. So 0 means it will just keep repeating forever. And that's usually what I pick. But maybe you only want it to, to repeat once, or to run 2 times total or 3 times total. So then you would change this value from, 2 to 3. Okay. You can make whatever you want, but 0 is a good place to start. Okay. And so then this is the code here that actually makes the animation. So again, the first, we define this variable that I'm calling maps list. And so we're using the pathlib module to grab all of the PNG files that correspond to that wildcard setting that we set up here. So basically, it's all the PNG files that have detections in the name that are in the maps path directory. So that corresponds to the map plots. Okay. Then we basically make a list, and we use the Python image library to open the image function to open each of those files. And then we string them together here, and we save them to that same map plots directory. Okay, so let's see. So did I run this? I'm going to make sure you run the first one. run this one first, and then run the second one. And it will, it's really fast. It will, like a second or two, it'll have made the GIF file. You might have to refresh, but there's our GIF file right here. Okay. So, you know, I downloaded it before, but again, you can, you know, download it to your computer or save it to your Google Drive. But if you double click on it, it'll open up, you just, like if you just want a quick view, it'll open it up in a separate tab. So you can at least just get like a quick view and see what it looks like before you download it. So there it is. Pretty cool, huh? I don't know, I think it's cool. I get excited. Okay. And then I think we can, yeah, close tab. You can close that. Okay, so the very last thing, so exercise 2. So I want you guys to do the same thing we just did, except instead of making the GIF of the fire detections, basically what you're going to want to do is you're going to want to modify the settings here in this first block, and then rerun this second block, and to make an animated GIF of the fire rated power map. So these 6 fire rated power maps that we made, I want you guys to make an animated GIF of those. Okay, just make sure you change these settings. Otherwise, you're just going to make a GIF of the fire detections again. Okay. All right. So take a minute. I'll give everybody a minute to do a minute or two to do that. Is anybody able to do it? Yes. Okay. At least one person. That's great. Okay. Looks like another person. That's great. Anybody else?
¿Alguien más pudo obtener el GIF? ¿Lo puede anotar en el chat, por favor? Okay, yeah.
Okay.
Oh, great.
Here we go. Okay, great. So what I would do for anybody who hasn't done it yet, I would change the wildcard from detections to FRP. Because again, I want to pull out just the maps, the PNG files that have FRP in them. And then I would change the save name. So change it from fire detections and make it FRP instead. Okay, and then rerun that block. And you don't have to, you know, do it exactly the same way, but, you know, something that's going to be, that you're going to be able to use to, you know, to grab all of the FRP files, and then with the name, make sure you name it something different from what we named the fire detections GIF. Okay. And then if we run it again, okay, it should, yep, there it is. So there's our GIF of the FRP. And if you click on it, I guess it'll take a second to load. There it is. Looks good. Okay. Does anybody have any questions? Close that. Any questions about anything related to the fire products, plotting the fire data, processing the fire data, how the ABI fire data are different from the VIIRS?
¿Alguien tiene alguna consulta acerca de cómo generar las imágenes, acerca del proceso de los datos de VI o de VIIRS? Pueden anotarlo también en el chat, por favor. I think everything is clear.
Okay, great. You still see my screen?
Yes.
Okay, great. Thank you. All right, so let's move on to the second section where we're going to work with the aerosol optical depth files. So the first thing we're going to do is we're going to find the GO16 ABI full disk files for November 6th at 13 to 13:59 UTC on the Amazon Web Services archive. So just the same steps we did for the fire files. So the first thing we're going to do is we're going to run this block. And the only thing that's different from what we did with the fire files is the name of the product. So the name for the AOD files is AODF here. Okay. And then when we run that, we're going to print out the files. And there's six files for the AOD. And they're the same time step. So 1300, 1310, 1320, 1330, 1340, and 1350 UTC every 10 minutes. Okay. And so then we're going to use the same two functions that I wrote that we saw previously to subset the files. So I just copied and pasted. This is exactly the same code that we ran before for the VIIRS files. So the only difference is now we've the files lists that we gathered are corresponding to the AOD files instead of the VIIRS files, the FDC. Okay, so if we run this, we'll see under ABI files that we're downloading the subsetted. So the first one should be there. So there's the first one. So this whole process takes a little bit longer than it did with the VIIRS files because the AOD files are much larger. So this is gonna, I don't know, I think it takes about a minute or so to go through all of them. Okay, so yeah, so mine took about 1 minute. So if I refresh, okay, so when yours is done running, you should see now you have 12 NC files under the ABI files. So you should have 6 that have AOD in the title, and then 6 that we already downloaded that have the FDC. Okay, maybe just everybody let me know when were able to subset and download the 6 AOD files. And just let me know when that everyone's able to do that. Okay, great. One person, thank you. Okay, great. Thank you. Okay, it looks like people are able to get it to run. I'll wait another minute or so because it does take a while for all the files to process and then save. The AOD files, the original files are quite large. Okay, is there anybody who wasn't able to download the AOD files? Do I need to wait any longer?
¿Alguien tuvo problemas en obtener los archivos? ¿Puede escribirlo en el chat, por favor? ¿O necesitan más tiempo o sigue procesando?
All right, so do you think we can continue, Laura?
Yeah, I think, yeah.
Okay, great. Okay, so now let's open the first file, the first AOD file that we downloaded. So again, we're going to go through the same process that we did for the VIIRS data. Whenever you're working with a new satellite product, you want to read the documentation, which I've done for you. So according to the README file for the GO16 ABI AOD, we're going to need to use the DQF variable to select the AOD data quality. So if you remember from last week, we want to use high quality AOD for quantitative applications, and then high and medium quality AOD. We call that top 2 qualities for qualitative applications. Okay, so and we use that with the DQF data variable. So let's open one of the files that we downloaded and see what it looks like. So again, we're just going to set the file name as one of the files that we downloaded. And then we're going to open it up using the Xarray open dataset function. And we're going to look at the metadata. Okay. So again, if we scroll down here, the organizational structure is the same as the VIIRS file. It's just, you can see there's even more data variables. So there's 62 data variables in the AOD files. So again, let's first look at the attributes. So again, these are the global file metadata. So if you scroll all the way down to the bottom, you'll see again, this is the comment that we added. So just information about how we subsetted the file from the ABI full disk files and using the indices of the Y and X variables that we found. Okay. All right, so if we close that, and if we come back up, and again, we look at the coordinates, we'll see again, we have this X and Y. So we have the GOES fixed grid projection Y coordinate and the GOES fixed grid projection X coordinate, okay, instead of the latitude and longitude. So that's exactly the same as we saw with the VIIRS files. So now if we open up the data variables, you can see there's a lot of them. 62 is a lot. But the ones that we need are at the top. So the AOD data, that's the one we need, the AOD file. So this is the aerosol optical depth at 550 nanometers. Okay. And then we need the DQF variable. So if you click on that, this is the data quality flag. Okay. And you can see the values are the same as the quality flag variable for the VIIRS data files that we looked at last week. The only difference is the name of the variable is different. So this one is called DQF. The VIIRS quality flag is called QC_all. Okay, but it's the same. The values are the same. So you can see the flag values 0, 1, 2, or 3. 0 is a high quality. 1 is medium quality. 2 is low quality. And 3 is not retrieved. Okay. Okay. So, and then there's a lot of other things that we're not gonna worry about. Okay, so if we scroll down, so again, same thing. I like to get a look at the data arrays. So let's use the X-array data array values to just take a look at the AOD data array first, and then the data quality flag, the DQF data array. Okay. And so we can see, again, this is showing the beginning and the end of the data arrays. So you can see most of the AOD data in the beginning and the end of the file are invalid or not retrieved. And those are represented by the NaN. And if you look at the DQF values, you can see actually where there's a NaN, that corresponds to a data quality flag value of 3, which means not retrieved. And the ones where there actually are values, like right here, that corresponds to, it looks like both of them are a data quality flag of 2, which means low quality data. Okay, so you can see how that works, the data quality flag corresponding to the AOD values in the AOD array. Okay, but again, because most of these are NaNs, I like to use the NumPy NaN min and NaN max to see what the maximum and minimum values are in this data file. And we can see they correspond from minus 0.05 to essentially 5. Okay. And so if we look back up here, well, let's look up here first. So if we looked at the metadata, where was it, for the AOD variable here, we can see here's the listed valid data range. But that doesn't make a lot of sense, right? If you remember from the slides and even from the VIIRS AOD last week that we worked with, the valid range is minus 0.05 to 5, but that's not what's shown here. So that's strange. So if we come back down here, where were we? We can actually, we just looked at the valid range, but we can print it as well. So again, we see the same thing, that the valid range is listed from 0 to 65530, and the data type is an unsigned 16-bit integer. But that's really strange, right? Because we're seeing, like, when we look at the actual data in the array, clearly they're floating point numbers. So what's going on here, all right? And so the reason that we're seeing this discrepancy is because the AOD data, ABI AOD data, are stored in the data files as unsigned integers, okay? So we can do the same thing that we did with the mask variable. We can print out the encoding, basically the information that was used to encode the AOD data when the file, the netcdf file was made. So if we scroll down, we can see, yep, the data type is uint16, so that's unsigned, or 16-bit unsigned integers. And we also see that there's something we haven't seen before. So there's something called a scale factor and an add offset that are included with the encoding, okay? And so what those mean is that, as I mentioned, to save space in the data file, because floating point numbers take up a lot of file space, so the AOD data are saved in the original netcdf file as unsigned integers. And then this scale factor and add offset are included. And so what has to happen is that when the AOD data are read, like when the file is open, you have to basically multiply the AOD data times the scale factor and add the add offset. And that converts the integers, the unsigned integers, to floating point numbers, okay? But Xarray automatically does that for us. So again, when we use the XR open data set, this decode CF equals true automatically has Xarray unpack any encoded files. And so it automatically applied the scale factor and the add offset. So that's when we actually look at the data themselves, like we printed out the data up here, the data array, and we looked at the maximum and minimum. That's why the AOD data appear as floating point numbers, because Xarray automatically converted them for us, which is great. That's super convenient. But it's a little bit confusing if you're looking at the, the valid range and the metadata. So what we can do is we can convert the valid range and the metadata So we can apply the scale factor, so we can multiply by the scale factor and add the add offset. So if we do that, it'll convert the valid range, which was displayed as integers, into floating point numbers. Okay, and that's what happens here. So that makes more sense, right? So now we know that the valid range of the AOD data is minus 0.05 to essentially 5. So even though this doesn't appear exactly as 5.0, we can round up. Python, I have the link here. Python has some inconsistencies in how it displays floating point numbers. So, okay, does that make sense? So essentially, if you see something like this, something strange, where something is being, like a valid range is being displayed as an integer, but you know the data themselves are floats, you should look for a scale factor and add offset. Okay. The other thing to mention is that Xarray does this conversion, applying the scale factor and the add offset automatically. Other programming languages do not do it automatically. So for example, if you use R or you use IDL, I know those are two languages that you manually have to do this. So you have to open up the data file, pull out the AOD data variable, multiply the AOD data array by the scale factor and add the add offset to convert from the stored unsigned integers to floating point numbers. Okay, so just be aware of that. Okay, does anybody have any questions about that? Okay.
Just a comment.
Oh.
I believe IDL, for example, has already some libraries that convert this, like in this case, for Python.
Okay, that's good to know.
Yeah.
Okay, so IDL will do it for you as well. Okay, good. If you select the right library. Okay, I'm fairly certain R does not. So that's just something to be aware of. If you use another programming language, you just want to double check and make sure that this conversion is happening. Marcos or Laura, could you please translate the question from Christian in the chat?
Yeah, it says the valid range, once it's corrected, is the same as the values.
That's a good question. So that just happens to be a convenient or a coincidence. So this here, the valid range, the converted valid range, that's the valid range of the AOD data universally of any AOD data. Okay, they only are they only range from minus 0.05 to 5. Now in this particular file, that also happens to be the range of the data in what we found here, the range of the data in this particular file. But that's a coincidence. You could have another file that didn't have AOD data that go up to 5. This, I think I showed at the beginning, this particular day, there was a lot of thick smoke over Bolivia. So there's very high AOD values in this file. Normally AOD is less than 1. But again, the thick smoke is having the AOD values go up to 5. But yeah, that's a great question, Christian. It just happens to be a coincidence in this particular file. Okay, great question. Any other questions? Okay. So another thing that we noticed, this is the same thing that we noticed with the mask data array when we were looking at the VIIRS data. So let me go back up to the metadata and look at, I'm going to minimize the AOD. So this is the data quality flag. So again, notice Xarray is saying that this is a 32-bit floating point number. But from the valid range and from the flag values, this looks like an integer. It doesn't look like a floating point number. So what we can do is, if we can scroll back down here, if I can get there, we can use that encoding, the data array encoding again, to check the data type of the DQF variable. And sure enough, it's actually an integer. So it's an unsigned 8-bit integer. Okay, it's not a floating point number. So we can, use the same approach that we used for the mask data array in the VIIRS files. So we can use this as type function to convert the DQF data array to the proper data type, which is UNIT8. So let's do that. Okay, and when we do that, we can see, now again, we can see the type is correct, and we can see that the values are showing up as integers in the data array itself. Okay. And then, so now that we've kind of sorted all that out, let's again use the plotting functions that are built into Xarray to make a quick plot of the AOD data. And I'm going to use the top two qualities AOD. So that's the high and medium quality data. And so we're going to do that using the data array Xarray data array where function. So we're going to say where the data quality flag array is less than or equal to 1. Okay, so if we do that, I'll take a second. Okay, so now we can get a plot to see what the AOD data look like. And again, this is a two-dimensional data array so that it has dimensions of the Y and X coordinates. So again, latitude and longitude aren't in the file. So when Xarray plots the AOD data, it's plotting it on the X and Y, using the X and Y coordinate values. Okay. All right, and it's nice, we can see the approximate range of the data. We can see there's a lot of data greater than 0, or greater than 1, corresponding to the dark red color. All right, does anybody have any questions? Okay. All right, so before we close this data set, I want to show you how to define the native geostationary map projection. So you remember last week when we used Cartopy, there's many different map projections that we can choose from. But with geostationary satellite data, I think it's nice to use the geostationary map projection. Because then we're mapping the data kind of the same way that the satellite is observing it and measuring it. So to do that, we can use information in the GOES imager projection variable that's in the satellite data file. So we have to define a variety of constants that are in the data file. So the height of the satellite, the semi-major and semi-minor axis of the Earth, and then the central longitude of the satellites. And we put those together and we define this variable for Cartopy called the globe. And then we use that information to define the geostationary map projection. Okay, so if we run this, we'll use this map projection when we plot the AOD data, which we're going to do next. So the question, is the offset a constant variable? The add offset, do you mean? So back here, where'd it go? The add offset? Is that what you're asking, Gerson? Yes. Yes. So this scale factor, so going back to converting the AOD data from integers to floats, the scale factor and the add offset, those are constants, yes. So when we do the encoding, we print out the encoding for the AOD variable, we'll see the scale factor and the add offset. Those are constants for the AOD data. That's correct. So they're the same for all ABI AOD data files. Yeah, that's a good question. Okay. Any other questions? Great questions. Okay. All right. So let's close that data set that we opened, that one file that we opened. And now we can move on and we can actually plot the AOD data on the shaded map background. Just like we did last week for the VIIRS data, we're going to use the same plotting function. Here, let me go down and talk about it. So we're going to use the same plotting function, the same setup for our figures. The there's really not going to be too many differences. So this should look very familiar. So at the top here, we're going to define this variable called quality. Okay, and this is where we're going to set either the high quality, the top two qualities, which is the high plus medium, or all qualities, which is the high and medium and low. And remember, using the low quality, we don't recommend that. But I just want to plot it today just to show you what it looks like, just like we did last week with the VIIRS data. So we can see the difference between the AOD quality for the high, the top two, and the all qualities. Okay. So then we're going to define the variable called file list, where we're going to, in the ABI files directory, we're going to get all of the AOD netcdf files. Then we're going to loop through the files, and for each one, we're going to open the file using X-ray. We're going to set up the figure, and then we're going to use the geostationary map projection that we just set. Okay, so we're going to have the geostationary projection of the GOES-16 satellite be our map projection. We're going to zoom in on the western or central western South America region. So just like we did last week, we're going to set up the latitude longitude grid lines using CartoPy. We're going to add borders, and we're going to shade the lakes and land and ocean polygons to make the map background. We're going to set our color map. Like we saw last week, I like to use rainbow and dark red, but you can obviously change this to whatever you would like. All right, so here's where we're going to process the AOD data. So first, we're going to convert the data quality flags to the correct data type, and then we're going to select the quality that corresponds to what we entered above using the data quality flags. Then we're going to use the p-color mesh plotting function, and we're going to plot the original two-dimensional latitude and longitude arrays that we calculated. Remember, way back before the break, we calculated those using that function I wrote. And then we're going to plot the AOD data quality using the AOD or the xarray.where. Whoops. And so then we're going to select either the high, top two, or all qualities data. And then we're going to add the AOD color bar. We're going to use the information from the satellite data file name to make a title for the plot. We're going to show the plot, and then we're going to use information from the file name to actually save the PNG file in the map plots. Okay, let's run that. And again, that'll take a little bit longer than the VIIRS files because the AOD files are bigger. You'll see these download warnings appear. And again, remember we saw this last week and in week 2. These download warnings, you can ignore them. They occur the first time you download the natural earth feature shape files, which is what we're using to create the shaded background. Okay. So again, as we loop through the files, the 6 AOD files that we downloaded, we'll see the 6 maps being formed here, being plotted. I can center these. There we go. Here they go. Okay, and then as they're created, they're being saved under our map plots directory on the Google Colab instance. Okay, and we started with the top 2 qualities because again, that's what I recommend for general applications. Okay, so it took 1 minute for my files to plot. And so you can see them there. So it's the AOD top 2 qualities. And then we can see 1300, 1310, 1320, 1330, 1340, and 1350 UTC. Okay. So you see the 6 plots there. Okay. All right, did everybody, maybe people can just let me know if they were able to run and get the 6 PNG files to save. Did everybody get the files to plot? Okay, there's at least one person. Thank you.
Me?
Yes, Marcos. Yes.
Yes. I got the files, but I also got a warning message.
Yes, sorry, I mentioned that. Let me mention it again, Marco.
Sorry,
So
I
every
missed it.
time, where did the warning go? Oh, wait, I hit it. Hold on, let me bring it back up. So every
Okay.
time, the first time that you use the Cartopy to do the shading, so it was, it's this step right here. So we're adding the coastlines and the borders to the map, and we're shading the lakes and land polygons. We're using the Cartopy interface to the natural earth feature shapefiles. And so the first time you use them, Cartopy downloads those shapefiles. And so it gives you this download warning. So you can just ignore that warning. It's that they're not, it doesn't impact the maps. It's just letting you know that you just downloaded some shapefiles. That's all.
So it's not really a warning.
It's
giving you
yeah, I don't know
information.
why they do it, but yes, it's a warning that's built in automatically, but it's nothing to worry about.
Okay, thanks.
Yeah. Let's see, there's a question. I want to compare ABI AOD to ABI AeroNet. So Odon, so somebody asked this same question last week. They wanted to compare VIIRS AOD to AeroNet AOD. And so the way you get the AOD values is somewhat complicated. You have to use the Habersign formula and draw essentially a circle with a radius of 27.5 kilometers around the AeroNet station. So the AeroNet station location is at the center of that circle. And then you average the AOD pixels that are within that circle. And then that's how you spatially match the ABI AOD or the VIIRS AOD to the AeroNet AOD. And then you have to match them temporally as well. So typically it's AOD observations within plus or minus 30 minutes of the AeroNet observations. So it's a multi-step process. And I feel certain that one of the NASA RSET trainings covered that, and Anna was going to look for that RSET training so that she could share it with everyone. So I imagine she's only joining us intermittently tonight, so that's probably something that we can follow up on next week or the week after. Okay. All right. So next question: if I try to join multiple files, is the time dimension? So you can't. Okay. So you can't join multiple files, Gerson. So I think you're talking about last week when we used the X-array open MF dataset function to open the VIIRS files, multiple files all at once. So that won't work, unfortunately, for the ABI files because there isn't a dimension that they can be opened on. So that's why we had to have the loop. We had to have, let me go back. So that's why we had to have this loop, and we had to loop through one file at a time and open each file one after the other. Okay. So yeah, unfortunately, there's not an easy way to use that X-ray open MF data set. That's a good question, though. I wish there were. Yeah. Any other questions? Those are great questions. Any other questions? Can AOD be measured at wavelengths other than 550? Yes, it is. It is, in fact, measured at wavelengths other than 550 nanometers. Typically, satellite data are reported, AODs reported at 550 nanometers because that's right in the middle of the visible spectrum. So that's the most commonly used wavelength for which AOD is measured. But for example, if you look at AeroNet AOD data, it's reported for 5 or 6 wavelengths. And if you dig into the AOD data file, the satellite data files, you can find AOD at other wavelengths. So yeah, it's just that typically the 550 nanometer measurement is the one that's most commonly used. Yeah, that's a great question. Any other questions? Okay, so let's let me scroll back down. So let's now make the GIF animation of our AOD files. So this is exactly the same code as we used for the VIIRS. The only difference is we're changing that wildcard because I want to grab all the files, the new files that we just made, the ones that have AOD_top2 in the name. Okay, and then we're just gonna, we need to make sure we change the name of the saved GIF file. So again, I'm just going to change the file and add AOD_top2. Okay, so if we run that, and then we run, so this is again exactly the same code to generate the animated GIF file. We run that. We should see right here. Here's our animated GIF. And if I click on it, it'll just open up a little thumbnail. Did I open? Oh, I think I opened. No, I did. Yep, that's right. So there it is. And I want to open up a bigger version. Did I close the bigger version? Wait, let me open it back up again here. Hold on, give me a second. I have it saved. Okay, so here's the bit. So when we get to the later time steps, watch down here. Do you notice how the AOD along the shore, it starts to retreat? Can you guys see this here? So, you know, AOD is being measured along the shore, and then it starts to disappear. See right there, boom, boom. Does anybody have any idea what's causing that AOD to be missing for the later time steps for 1340 and 1350 UTC? Anybody know what's causing that artifact?
I doubt that it is really real AOD, Amy.
No, it is.
It is, but it's almost in the Andean region and the
yeah. Well, so let's talk about this in a second. So that's not real, but this along here is along the coast. Do you have any idea? Do you know, Marcos?
You mean the blue one?
Yeah, the blue. So see how the blue starts to disappear? It's right there. See how it's disappearing?
No, but I think it's an artifact. I think it's looking at clouds more than, you know, it's over the ocean, the Pacific Ocean. There is
yes, it's over the ocean. Yeah, so this is actually the sun glint right here.
Oh, okay.
So here it's AOD, but as the sun starts to move over in these last two time steps, so the missing AOD is being caused by the sun glint right there and there. So that's just one thing I wanted to point out. If anybody's kind of noticed that, because it looks like an artifact, right? It looks weird where the blue AOD is starting to just disappear. So that's the sun glint. That's the reflection of the sun on the surface of the water at the same angle that the ABI sensor is looking down at the surface. So when that happens, there's no aerosol optical depth retrieved. And then the other thing is, yeah, Marcos, like you pointed out, this very high AOD along the Andes. So likely this is an artifact. So we talked about this, I think, in week 2 in the slides. So the aerosol optical depth algorithm was updated in early February 6th. And so it uses a different algorithm now. So this artifact, this high AOD over the Andes, is reduced now compared to what it was last November. But sometimes you can still get erroneous high AOD retrievals over the Andes, just because they're a bright reflective surface. So when people are looking at the AOD, you should just be wary of interpreting these data here along the Andes. Okay, these are all correct, but these are likely anomalous. Excuse me. Okay.
But you think that the bluish thing that you're showing us is real?
Oh, the blue along the coast? I think so. You don't think so?
No, what could be causing the AOD? Because that's a value, I don't know, 0.
Yeah, it's low. Yeah, it's going to be very low. It's going to be close. So that's clean air along the coast.
Okay.
Yeah, there's no reason just looking at it for me to discount it. I think it's probably real. But yeah, you're right. There are a lot of clouds here. So it's just, you know, it's measuring the AOD in between the clouds, and it's clean. But this, like a lot, once you get along the land with the Andes, that's not real. But this part.
So Gersten is saying that that might be crop areas, and that's true, but they. Okay, we can discuss this later.
Yeah, sure. You guys know a lot more about your region than I do, obviously. But this, for sure, I can tell you, this right here, this is the sun glint. So
yeah, that makes sense.
When we get to 1340 and 1350, that is that missing AOD that's expanding slowly to the west. That's the sun glint region. Okay, great. So, all right. Hopefully, everybody got that GIF to make or to generate. So, what I'd like you to do next is 2 steps. First, come back to the, if I can scroll up here, the code to plot the ABI AOD data, excuse me, and change the quality from top 2 to high, and then rerun this block. You can do that as you're doing it. And so that's going to generate the high quality AOD images. And then when those are done, come back and change this again to all and generate the all quality AOD plots. Okay. And then when all those are done being generated, come back down here and make GIF animations. Make one animation of the high quality AOD plots, and then a second one of the all quality plots. Okay, so I'll give everybody that'll probably take a few minutes. Give everybody a chance to do that. And just be aware, so the high quality plots will be faster than the top 2, but the all qualities will take the longest amount of time. I think they take 2 or 3 minutes total. And that's just because you're plotting a lot more AOD data for each of the maps that you make. So just be aware the all qualities data plots will take a while, take longer to generate. Yes. Okay, Gerson. So Gerson asked a question about the conversion of the DQF to make it the correct data type. Can you explain why not? Oh, integer. Okay. So let me go back up and explain that. Let me find it. Hold on, where we are. Okay. So the reason why is, it's for the DQF. Okay. So the reason why is, so I'm back up at the part where it says convert the data type of the DQF data array. So do you remember how we used the X-array data array encoding command to print out the encoding for the file for the DQF variable? Okay, so when we did that, we see down at the bottom, near the bottom, we see the data type listed for the original file, the DQF variable. And so the data type is UINT8. Okay, so that's why I used UINT8, which stands for 8-bit unsigned integers. Okay, so that's why here I used UINT8. Okay, does that make sense, Gerson? Okay, super. Yeah, so the encoding, this is where you find the correct data type for the particular variable. Okay, and then all you do is you just take that and you apply it to this as type command. So that way you're converting the data array to its correct data type. Okay, yeah, great question. Okay. So let me do all quality. Okay. All right, have people been able to get the high quality and the all quality AOD plots?
Amy, I tried to use the all option to use all the data, and I changed the wildcard to AOD underscore all, and then also in the animation name.
Yes.
But that's the only thing that I guess I need to change. But when I try to run the second part, it's giving me an index error.
Oh, so did you actually generate the all quality PNG files?
Ah, that's a problem, of course.
Yeah, that's why, because it's trying to find them and they're not
yes,
there.
Of course.
Yeah. So then just go back up to the plotting, the very top of the plotting function, and change the quality to all right here. And then rerun that, and you'll make the 6 all quality PNG files.
And this is what is going to take like 3 minutes, right?
Well, so yesterday when I did it, it took 2 minutes. Today it only took 1 minute. So maybe it'll be a little bit faster for you. Maybe my internet connection was slow yesterday for some reason. But yeah, in general, it should take a little bit longer because you're plotting more AOD data. So it should take a little bit longer, but hopefully not too long. All right, was anybody able to get all the way through and make the animated GIFs for the all quality and the high quality AOD data? Anybody have any questions? Marcos, did you get it to work?
Yeah, it worked.
It worked? Okay, fantastic. Yeah. Okay, so I have all the, let's just take a look. I just want to compare them. So this is the high quality. So again, you can see this is the highest confidence data. So you can see there's a lot more missing data, especially over where clearly where the smoke is. And there's more kind of missing data. You can see here, where it's the kind of the moderate thickness of smoke. And again, that's just because the screening for the high quality AOD data is very stringent. And then if we compare that to the top two qualities, which we saw before, oops, oh, I have too many things open. Hold on. There we go. This is the top two qualities. So we can see a lot of those, there's still some missing data, but there's a lot fewer gaps than there were compared to the high quality. But we do see more of those anomalously high AOD values along the Andes. So we're filling in with the top two qualities. We're filling in some of the missing data, where the smoke is, but it's coming at the expense of some of this, a few more anomalous AOD values. And then if we look at the all quality, which is right here, now we can see a few things. So we filled in a lot of the missing AOD, but you can see it looks, there's these kind of spots of high AOD mixed in along where the edges of clouds are. You can see some strange things happening in the very center of the plume. It looks like there's actually very low AOD values kind of in the middle of the smoke plume where the AOD is greater than 1. So that's definitely not right. That's an anomaly. And then you can see there's a lot of high AOD values along the Andes, which, are definitely anomalous. So that's why we say not to use the low quality data, because you have so many, anomalies that you can't really reliably interpret the low quality AOD data. So remember, use the high quality only if you have quantitative applications, and then the high and medium, the top two qualities, for qualitative applications. Okay, and then that's the last bit here is a reminder that if you, you want to save any of these files that you made, like the GIF files, for example, you just need to make sure that you either download them to your local computer, or you mount your Google Drive and download them to your Google Drive. Okay, because when when we close this out and we come back, Google Colab will reset. So all of these files that we generated and all the files we downloaded will be lost. Okay. Does anybody have any questions about the AOD data or anything that we covered today? Marcos, any questions?
Actually, I have a comment.
Okay, sure.
I think you really show us very interesting and very useful tools, but we need to realize that it's not only plotting. We need to understand what the data actually is in terms of the physical values and meaning, and that's probably the most important part from here. But the first thing is to be able to plot and to work with the data, right? So that this is the really big step. But for everybody else, I think I think we need to understand what the physical meaning of all these variables and things that the data is providing really means.
Okay, well, I tried to cover that in the slides.
No,
So
well, I'm not saying. I'm not saying that you did a fantastic job. I'm not. Look, what I'm
okay.
saying
I want to make sure I was giving you all the information that you need.
You are.
So.
No, but
Okay,
the point is, you are giving us the tools and what the data is related to, but all these things have caveats, that different things, and
yes.
So if we want to do a bit of science from this, we need to really learn more about the data itself. That's the point that I was trying to make. I don't know if you agree with me.
Yes, no, I agree. And again, that's why I suggest reading the documentation from the science teams, because that will, help you understand the caveats, and make sure that when you do apply the data, they aren't being misinterpreted. Yeah, I agree. And you may well, Marcos, you and your colleagues may have suggestions or feedback for the science teams that will be very valuable, because you live in South America, and you have a lot of different terrains in your countries. So I think you could provide valuable feedback to the science teams on how the data, what the performance of the data is in your region.
Yeah, and things like Odon, for example, is trying to do in Peru, that would help to the science team as well, I think.
I think so too, yes. I agree. And I regret that I can't share the matchups code with you. So there were questions last week, and I think it was Odin who asked how to do the matchups with the AirNet data. So my supervisor doesn't want to want me to share that code, but like I said, I'm fairly certain that it was covered in a previous RSET training. So hopefully Anna can kind of dig that out and share that with everybody.
Do you know if there is a publication of about this way? Because this is basically a way of validating.
Yeah, I can share the publication, like the methodology. I can't share the actual code to do it.
Okay. Because must be a reason to take like these 24 kilometers.
Yeah,
I think you
27.5 kilometers. Yeah, okay. I can. I have all those publications, so I'll get those and I'll put them in the classroom. How's that?
Oh, that's great. That's great.
Okay. Yeah. And again, I can outline the method, like what you have to do in the code. My supervisor is just sensitive about sharing the code.
Okay. So are there any more questions or anything else we need to cover?
So Anna, Laura suggests that I cover the homework.
Okay.
Review the homework. Do you want to do that?
Yes, thank you.
All right, I opened it. Okay. So can everybody still see my screen?
Yep.
Okay. So I think it was it homework 2? Was that correct? Where the participants were asked to download 2 sets of files. So what I did is I just made a new notebook that will just kind of go through the sections that we need to use to download those files. So the first thing, we just need to make sure we install the S3FS and the NetCDF4 packages. So that'll just take a few seconds. So again, you should be able to use everything from the week 1 tutorial. All I did was just copy and paste those cells into this new Google Colab notebook. I didn't write anything new. I just copied and pasted. Okay. So then we need to import our modules and packages that we're going to use. Okay, and then as always, I like to make new directories on the Colab instance. So you had to download a set of VIIRS files and a set of ABIs files. So I made a VIIRS files and an ABI files directory. Okay, and then again, I like to name the paths just for convenience. So we're going to be downloading the data from the NOD, the online archive. So we need to use the S3FS package to, where is it, right here, to connect anonymously, just like we did earlier today when we downloaded the ABI files. Okay, so the first question on your homework was to download VIIRS AOD data files from the SNPP satellite for April 28th, 2024, over the same geographic region that we've been using for all 4 weeks. Okay, so if you remember, I wrote a function that will for a specified satellite and date, we'll find the times when that satellite passed over the geographic region that you define. So let's just run that function. So all we have to do is copy, the function doesn't change, we just copy and paste it, we run it. And then down here, these are the variables that you have to change, okay? So in the training, we looked at the NOAA 20 data. So here we're looking at the SNPP data. So we're just changing this bucket name so that it's corresponding to the SNPP bucket now, okay? And then during the first week, we downloaded some VIIRS AOD files. So this is the product name for the AOD files. And then we changed the year, the month, and the day to correspond to April 28th, 2024. Okay, and then all of this is exactly the same as what we did in the tutorial. So if we run that, okay, we're going to see this is getting all of the files, all of the SNPP VIIRS AOD files that are available for April 28th, 2024. So it's over 500 files. It's all like global coverage. It's all the files. So then what we want to do is we want to use the function that I wrote to subset the files to just get the ones that are over the Central Western South America region. So again, to do that, we have to define, we want the SNPP satellite. Here's our observation date in year, year, month, month, day, day format. And these are the change. This is our bounding box. The boundaries, that's the same as what we did in the tutorial. And so then when we run this, you see we're going to get, so these are the times when SNPP entered and exited that region. So there were 2 overpasses. So SNPP entered the region at 1645 and exited at 1826 UTC. Oh no, sorry, backwards. 1645 and exited at 1652, and then came back again at 1826 and exited at 1833. Okay, so we're going to use those start and end times to subset defined from the 556 total AOD files for April 28th, 2024. We're going to just find the ones that correspond to these time periods. Okay, and that's what we do with this block right here, this matches code. Okay, so if we run that, so it turns out that I think it was just a coincidence that there happens to be 10 files. Yeah, it happens to be 10 files. There were 10 files in the example that we did in week 1. So I think that's just a coincidence. But anyway, so there's 10 files. You can see that they correspond to the SNPP satellite. We're printing out the file sizes as well. You can see they're quite large. Okay, and then once we have those 10, the file paths here for our matches, then we can use the fsget command to actually download the files to that VIIRS path that we defined. So if we run this, VIIRS files, they're big, so it's going to take maybe, I don't know, 30 seconds or so to download all of them. But here they come under the VIIRS files directory. Okay, yeah, so it took about 30 seconds from my computer to download them. So there they all are. Okay. So again, the things that you have to change, you scroll back up. So this function, the function I wrote, that doesn't change. That's always the same. Okay. What's going to change is first you have to get all the global files. So the bucket name may change. That's going to depend on what satellite you want. And then the product may change. Again, that's going to depend on if you want AOD data or the VIIRS data. Okay. And then the observation date, the year, the month, and the day will change depending on what your observation date is. Okay. Then this is where we're subsetting those files. So the satellite name will change. The observation date will change. If you want to have a different geographic region, then these variables, you'll change those as well. Okay. But then this is exactly the same. And then this is the same. Those 2 don't change. Does anybody have any questions about the VIIRS data? Okay. All right, so let's look at the second question. So the second question was to download the Go16 ABI, the FDC, the VIIRS full disk sector files for the same date, April 28th, 2024, for 1600 to 1659 UTC. Okay, and I said don't subset the file. So just download the original files because that's just a little bit easier. Okay, so this, the downloading the ABI files is a little bit easier because, we don't have to worry about global files and then just pulling out the files that correspond to the geographic region. Okay, because every full disk file covers the same geographic region. It's the entire hemispheric disk. So what we're going to do is use this code to grab all the files that correspond to, so again, this is our satellite. That's not going to change because you guys are always going to need Go16 because that goes east. The product name will vary depending on if you want the VIIRS files or the AOD files. And then you'll change the year, the month, and the day to correspond to your observation date of interest. And again, the hour, this is the hour of the range of when you want your data file. So in this case, we want 1600 to 1659. So the hour is going to be 16. Okay. And then remember, we have to convert to the Julian day because the ABI files are organized using the 3-digit Julian day. And then we're going to find all the files that correspond to this particular day and hour. And then we're going to print the names and the file sizes. So when we do that, we see there should be 6 files, and there are, and these are the VIIRS files, so they're relatively small. And then all we have to do is run this code to download the files. And they should be under the ABI files. There they are. Refresh. Right, 1, 2, 3, 4, 5, 6. They're there. Okay. Anybody have any questions about that? So again, if you're downloading ABI files, the only thing you need to do is you need to change, possibly change the product name, and then the year, the month, and the day of the observation. Okay. And then as we saw today, if you want to subset the files, which I would definitely recommend for the AOD data, then you run those additional functions that I wrote that we used earlier today. You run those, and that will download the subsetted files instead of the original files. Okay. All right. So that's all I have. If there's not any more questions, we can end a little bit early. Oh, the question. Vertical humidity profiles related to what ABI takes is the surface altitude. Yeah, Ludwig, you can definitely ask me offline. I am not familiar. I'm not part of that science team, but I can try to find out, get you a point of contact so that you can email the science team that's responsible for that product. Yeah, so definitely contact me offline and I'll see if I can help. Sure, no problem. Okay. All right, well, thanks everybody.